In this course, you will learn machine learning without libraries. Coding without libraries is the best way to learn the inner workings of a machine learning system, and it will help you greatly improve your software development skills. Dr. Radu teaches this course. We already released his No Black Box Phase 1 course. This is Phase 2, but you can still follow along even if you didn't see Phase 1. In this course, you will learn how to implement classification methods, such as neural networks, to recognize drawings. You'll also learn about data cleaning, confusion matrices, geometry, and the difference between vector and raster data. If you want to learn how common machine learning algorithms work under the hood, this is the course for you.
Hi, and welcome to Phase 2 of the No Black Box Machine Learning course in JavaScript. The goal here is to take the drawing recognizer we built in Phase 1 and improve its accuracy by implementing more advanced methods. Now, if you didn't complete Phase 1, you may be okay starting directly with this, especially if you already know some basic machine learning concepts. I will explain our code base briefly in the beginning, so try to understand, ask questions below or on Discord, and if all else fails, then go to Phase 1. This time we'll learn about data cleaning. It's a tedious process, but I'll teach you how to build a tool to make the job easier. Then we'll learn to visualize a confusion matrix, a special kind of table that helps us understand our model even better than the chart we built last time. It will be especially helpful when working with more than 2 dimensions. Speaking of which, so far we've only been using 2 features, but the k-nearest neighbor algorithm is not limited to that. All it needs is the way to calculate the distance between data points, and I'll teach you how to do that in 3D, 4D, 5D, any D, really. I'll show you an intuitive way to think about multidimensional spaces and distances, and we'll use up to 400 dimensions in this course. We also study another classifier, the neural network. We'll use the same code from my self-driving car course, because I want you to understand that machine learning methods are general techniques and algorithms we just apply to solve different kinds of problems. Now, this is more complex than that self-driving scenario, and our optimization strategy there wasn't really good. So I should teach you something better, like backpropagation, but I don't know how. I tried to come up with a lesson, I just can't seem to add anything to those out there. So I'll teach you how to train the network in Python, and then take the resulting model and just use it in JavaScript. So Python will do the heavy lifting, and our JavaScript app just benefits from it. Am I cheating? Maybe a bit. But I think that learning this is possible is a really important lesson here. You'll see. Finally, I'll demonstrate deep neural networks as well, so I don't get many comments about it. Now, I need to stress, this course is supposed to be a learning experience. I want you to understand how machine learning works and why we do the things we do. We use the data you helped me collect, so we have a real challenge, not some textbook dataset, and we use JavaScript because it's a high-level language where we don't need to worry about the small things, and because we can use it to build nice user interfaces that we can share without the need to download, install, and so on. I really hope you learn to build real things, not just something that reads from files and writes into the console. Another reason I use JavaScript is because it's not well known for machine learning. But many people do know JavaScript and want to learn machine learning. So if this is you, you found the perfect course. And if you don't like JavaScript, take it as a challenge and implement the same things in something you like. We don't use libraries, so it's really doable, I think. Sound good? Okay, then if you plan to follow along, take the starting code from GitHub. It's similar to the last one from Phase 1, but a little bit different. I've added your homework submissions and made a few other optimizations as well. Also, remember to get the data from this link. Place it next to the code like this, and you're ready to start. The first thing we'll check out is the drawing app we use to create new data. Here inside the web folder, and creator HTML. If you open this in the web browser, you'll see it looks quite different from before, but the functionality is still the same. It's going to ask you to enter a name here and then to draw several things. But the style is different because Ninja Coder did homework too, and I adopted his style. You can see these changes here in Style CSS, and everything I've marked as new style, starting from beginning, are things that he has added, and I commented out previous styles I've used. In case you're curious how to do different styling, I kept both here for reference. Now you'll also notice this compatibility section here at the top, and that's because in homework 1 I asked you to test the app and let me know how it went. There were some problems on iPhones, making the screen scroll when you want to draw. I got a suggestion from Meso to set touch action to none. Aaron commented that these should be set to none as well for it to work. Really not sure if these are enough because I don't have an iPhone to test, but I also got feedback from MJ and Rick, and they said that I should go here in the Sketchpad component and add prevent default to the pointer events, which, by the way, Kelvin said I use instead of the mouse events and touch events separately. I really don't know if these comments help, because when I test on mobile, it works just fine. But please let me know if it works for you. I've added these changes on the version of the app on my website that I still use to collect data if you want to submit, and also in the recognizer that we'll build by the end of this course. Now, after you're done with the drawing and press next, you're going to get the option to save this. And it's going to create this file that contains all the information about the drawings you just made. It's a JSON file that, if I'm going to format like so, contains the information about the student, some unique identifier, and then the different drawings, the 8 different drawings, each of which are made of a collection of paths containing points. So this is the XY coordinate of the points. And this here is one path that is used to draw the car, and this is another path of the car and another path of the car. So the car I drew had 3 different paths, and then the fish and so on. A quick note here about downloading this JSON file. Marcus suggested I set here application JSON, otherwise there could be some problems. And Godlike Mouse pointed out that I don't need to add this anchor here in the body, and it still worked just fine. Now, all the data I collected from you has the same structure as this one right here, but it's inside of this data folder, and there are a bunch of them. 716 of you made drawings, so that's a total of 5,728 drawings. And we can visualize these drawings using this other app that we built. But if we open this viewer HTML in a browser, we see that nothing is there. And if we open the console, there are some errors. And that's because we need to run some scripts to get things started. These are here inside of the node folder. We open a terminal. I took Diego's advice to use the terminal from here instead of command prompt. Change the directory to be inside of this node folder, and let's make sure that we have node installed. And we do. If not, you're going to have to install it. And then you can run npm install inside of this folder, and it's going to automatically run all the scripts that we need. It now generates a dataset by running this script. And what that means is that here inside of the data, we don't have just that raw folder anymore. It created a couple of new ones. The dataset folder contains 2 subfolders. The JSON folder contains 1 file per sample. So now these paths here are for 1 drawing. The same drawing that you can actually see here in the image folder if you open 1.png. There is a car here, but because it's black and with the transparent background, doesn't look very nice. But it's okay because all our scripts have finished now, so we can investigate this data in the viewer HTML after we refresh it. You can see how Ninja Coder's style looks here as well. I like this dark mode. I think it's better on the eyes. Now, what we see here on the left are many people, the 716 who have made drawings. The drawings are here in one row, and if you click on one, you can see its features on the right highlighted on the chart. Now these features, the width and the height that we extract, are the features of the bounding box. If I drag this item up here like so to see it better, this is what the width means and this is what the height means. So this car has a much larger width than the height. Seems to be about double. Now, if we scroll down here about halfway, we're going to see a new section starting called testing. And here the labels that you see written are what our machine learning system thinks that they are. The blue highlights are the correct ones, but the others are wrong. And here, if we are going to click on something, for example, this pencil, we will see a different kind of highlight here on the chart. Let me zoom in a little bit. And just to make things clear, I'm going to click on this pencil a few more times. And notice that it's not originally there. It's a new point that we've added now, and it's categorized as a pencil because its nearest neighbors, the majority of them, are pencils. Here we use 50 nearest neighbors, and I'm drawing a connection to all of them. So based on the majority, our machine learning system, the k-nearest neighbor classifier, categorizes this as a pencil. But sometimes, like this guitar, for example, seems to be a house. Let's figure out why. It's quite hard to count, but you can probably see quite many houses here in this area. So it is a house. Our accuracy is not that good at the moment, but I'm going to teach you how to double it by the end of this course. There's also this button here for opening the sketchpad. And here you can draw something live, and in real time you're going to get the classification. If you zoom out, you're going to see this drawing that we made here and all of its nearest neighbors. And in this case, the majority are pencils. But maybe if we're going to turn this into a tree, now this has changed. And the new majority seem to be trees. We've built some really nice tools, didn't we? One more thing I should remind you of is that we also have this decision boundary plot, this colored background right here. We can use this decision boundary plot more effectively if we go inside of the viewer here and pass the testing samples instead of the training samples to the chart. So now when we refresh, well, okay, things look quite different. The decision boundary is only on this side, but that's because we have this one sample here from Erminio, which I suspect actually has a really, really long width, and it was some glitch in the drawing. So for that reason, it has about 2 width instead of a maximum of 1. These are normalized. Anyway, now when we look at these testing samples here, if they lie on the same color as the decision boundary plot indicates, they are correctly classified. But if they don't, like this one right here, then it means that it's a wrong classification. So anything that looks colorful on a different background, it's a bad classification. Like this is apparently a guitar. Let's review a bit how these scripts work in the node folder. The dataset generator is creating necessary directories if they don't exist yet, and then it's generating this new form of the dataset. It's going through each of the samples one by one, and it's writing them in a new file and also generating an image for each one. This is the function from down here. Now, feature extractor is going through the samples one by one and extracting features as specified by these feature functions in use. You can find these feature functions in the common folder at the top, right here. And there are several functions defined here, but in use, we just have the width and the height functions that I mentioned previously. These two are not used at the moment. They could replace the width and the height here, but these are just much better, so we keep them for now. Now back to our feature extractor JS. After we get these functions, we call them here on the paths of every sample one by one and extract the data point. We then split in training and testing, half and half, and normalize the data to be between 0 and 1. And then we just write the output files in training and testing respectively. And there are 3 formats here: training, training JavaScript, and training CSV. And same for testing. You can find these in the data, dataset, and they're right here. The JSON files are here, and the CSV files are here. And the JavaScript files are up here in JS objects, testing, and training JS. They are the same information written in a bit different way because I want these to be accessed by our scripts here, but also by our web page, and also by the Python scripts that we have here. That's what the CSV is for. And yeah, I know Python can read JSON too, but I've seen so many people use CSVs in Python, and I think it's a common practice, and you should know about it too. So if I'm going to open here testing JSON, and I'm going to format it here, you will see first the feature names, the width and the height, and then all the samples here. Car, fish, house, tree, bicycle, guitar, pencil, clock, and then another car, fish, house, tree, and so on. All of the 2,864 samples are listed here in this long array. And the point is just the width and the height values for each of these samples. You're going to find the same information here in testing CSV, but here it's a different form. The width and the height, and then the label here. It's something you could easily paste in Excel as well. And the JavaScript file here at the top is the same as testing JSON, but with this in front of it. It's creating essentially a global variable called testing with this content here. And I'm not particularly happy about this code structure. It would have been much better to use modules here and make them read JSON. Actually, Rumach suggested I do that, and I recommend you try what he says there. The problem for me is that if I use the live server extension, for some reason everything starts lagging on my computer. I'm not sure if it's just me or for some reason the code we're writing doesn't work in general with the live server extension, but if you do try it out, let me know how it went. Now, going back to these node scripts, the last one is run evaluation, and it's going to use the KNN classifier here, built using the training samples, and it's going to classify the testing data and compute an accuracy. It also generates this decision boundary plot and stores it here in data models. This is where that image comes from. Now, this image is a low resolution here because when running this script, this part is quite slow. It's going to generate that color for each individual pixel. And the size of this image is 100 by 100 pixels, but that means 10,000 different pixels there to calculate. And for each pixel, you need to calculate the distances to all of the nearest neighbors. And that's a really intensive process. So if you want to set here a bigger value like 5,000, this decision boundary plot is going to look much nicer, but you're going to have to wait a few hours. But you're in luck, because if you want to see how such a decision boundary plot looks like, you can open up this resources folder And it's this one right here, KNN 50. You can replace the one from here if you want to see it in action on the web page. And refresh. And now it's much sharper, and you can also zoom in to see how the edges look like. Now, before we get into implementing new things, I have to mention this chart right here. I've implemented a more optimized version of it. If we close these things and open the chart from the web folder, the optimization I've done is that from the chart homework. Nobody did it, and I can understand why. It's kind of challenging. But I did point out what I did here and there, and you can compare with the previous code if you're curious. Basically, if doing something like maybe updating now this point here, the one that we are drawing, I'm not redrawing everything all the time. It just updates this one drawing on an overlay canvas on top of the previous one. I did get one optimization for the scaling, which I've added here. This was suggested by Peter. And I also want to point out improvements I got to my prerequisite videos about 2D vectors and trigonometry from Christian and George. Christian rewrote the code in an object-oriented way and used Bootstrap, and George tells us how to make it work if you scroll with the magic mouse on Apple devices. Also, one funny thing that happened is that these emojis now are different than before because I got Windows 11 on my operating system and they changed a bit. I recolored them a little bit differently here with the filters, but they would have been just fine otherwise as well. Quick mention to this Python folder here. So if I'm going to start the terminal now and go to Python folder and type Python KNN, we're going to get the accuracy here as well. But the code there is really small, like this is it. Because we use the scikit-learn library and we import the k-nearest neighbor classifier from there, read the data from our CSV files directly. And this is actually done here with the read feature file function from the functions py. And the Python is not really adding anything into this project. It's just showing you another way of doing things with libraries, which is common, I think. Now let's begin to implement a way to do data cleaning. And speaking of cleaning, I reformatted all the code to use spaces now. And we are going to be testing on a different window like this. I got a lot of bad comments saying I should use spaces. And now with this larger window here, I have room for that. Now, data cleaning means that we are going to throw out some samples which make our model bad for some reason. For example, here, this is a drawing of a guitar, but it looks like some kind of mistake. And same for this pencil here. We can also see maybe here, this one, this is not the drawing of the car. It's a drawing of a bird, I think. So small things like that are probably ruining the model in some way, I'm going to want to throw away. It's very tedious to start writing down which samples need to be removed. So I'm going to build a tool that allows me to click on the samples here and remove them. You'll see. But now the clicking is implemented already here in display.js, right here where we click on the sample container. And we should inspect the event we get when clicking here to see if we can figure out how to maybe control click on the item and do something else instead of this handle click function. So I'm going to type here EVT for event, and now I'm going to open here a curly brace and close it like this because we're going to write more things. Let's begin with the log in the console, logging this event, saving the file, and now refreshing the page, and I'm going to open the console and click on something here. And you can see now the event is printed here. If we look at the properties, we will find this control key that is set to false. And if I hold now control when I click on something and scroll down here, we will get another print of the event, but this one has control key set to true. So that's how we're going to distinguish between the two. Let's remove this line and check if the control key is on. We are going to toggle the flagged sample because I want to flag something when I click on it like that, but I also want to unflag something in case I did a mistake. I don't want to refresh the whole page if that happens. So otherwise, here we're going to say else and put this handle click in that case. Now, this functionality for toggle flagged sample will be implemented in a new file. I'm going to call this data cleaner. So let's open our viewer here and import this new file, data cleaner, and create it here inside of this JavaScript folder. Data cleaner.js. Here our flagged samples are going to go inside the list, which is empty for now, and our function for toggle flagged sample, given a sample, is going to do the following. It's going to check if the flagged samples includes the ID of the sample, and if so, we will remove it. I first get the index of this sample that we clicked on, and then I'm going to remove it by using the splice at the given index, removing one item. Now, if we clicked on something that isn't yet in the flagged samples, we just add it there using the push method, like so. And now we want to visually emphasize which items are flagged and which not. We're going to make a flagged class that is going to be added to all the flagged samples. And every time we click on something, we remove the class from everything and then add the class to those flagged samples, kind of like a refresh mechanism. So let's first remove this flagged class from all items that are flagged, like this, using a for each loop so that each item's flagged class gets removed. And then re-added like so. We are going to loop through the flagged samples, get the element using getElement by ID, the sample with that ID, and add this to the class list, like so. So this should work. Only thing we need is a new class called flagged, and we're going to be adding that in styles.css, and I'm going to be doing it here at the bottom of the file. It's just going to be marking everything with a red color, and I'm using here important because I want it to be on top of the previous style. Let's save this and now refresh. And clicking things normally works as before, but control clicking gives us this flagged view. And if I click again on the item, it's going to go away. So let's start flagging here the things I pointed out previously. And I'm now going to go through all the things and mark down anything I see suspicious. And I'm done. It took much longer than I thought it will, but it's over. And I basically mark down things that are incorrect or don't look at all like what they should be. This should be a bicycle, but somebody drew a house here, so sometimes these things happen. And Pi just drew mixing things up. I think they wanted to see how the system handles those cases. But most of the data is quite good, and in total, I think there is probably about maybe 200 or so flagged samples. This is a funny one. This is supposed to be a house, but many people drew a horse there instead, like Jin. And I think this has to do with psychology. And basically, house and horse are very close when you look at the letters. And I asked you to draw a house after a fish, so it's after another animal. And without a context, just being told to draw this, then you might read horse by mistake. And Jin is not the only one. There are actually quite many horses here in the database. And that's funny because it reminded me of this Mandela effect. If you don't know what it is, I'm gonna link it in the description. But basically, there are things that people remember differently than what they happened, and there are things that large groups of people remember something differently than what actually happened. And this could be one example of that. Like if we're gonna group together everybody who has drawn horses here, and we ask them what were they supposed to draw, they will definitely remember the horse being asked, but I never asked anybody to draw a horse. I asked for a house. Anyway, let's have a look at our flagged samples. So I'm going to type this in the console here. And there are, actually close to 300 of them. So 300 flagged samples. That means we have 5,445 to work with. And one thing I really need to mention here is that I actually flagged samples also in the testing set. And normally you don't do that, because testing should be as natural as possible, and we only want to do the flagging in the training data, which we use to create our models. But I did it because I don't think it's going to impact on the accuracy that much. And I think that the people who have made those drawings that are messed up on purpose will not expect the system to mess up as well. So normally that's not needed. But also because I don't want to do this again anytime soon. And if more data comes, then a lot of them are going to be flagged already. So yeah, just keep in mind that normally you don't touch the testing samples. Now, this array here is quite long, and I would like to copy it somehow. I'm just going to write here JSON stringify the flagged samples. And this is going to display all of it here as a string, like so. I'm going to copy it and go into common and utils, and under the flagged users, which are people that have drawn some bad stuff, I'm going to add here flagged samples. And I'm going to paste here what we got and remove the string syntax from there. And now we're going to use these flagged samples when creating the dataset to omit them from the raw data. We'll still keep them in the raw data for reference, but we won't be using them in any of our tasks. So let's go here inside of our node folder and dataset generator, and right here a line in this for loop that is going through all of the samples like so. If the sample is not flagged, so if the flagged samples doesn't include this ID that we are generating here, then we do everything for it. Write it in the new file and generate the image for it here. Like so. And now we can run this dataset generator using Node. So I'm going to start the terminal, go to the Node directory, and type here Node dataset generator. You can put JS if you want, but it will work like this as well. And now those samples that are problematic should be omitted from our processing. Now, after this script is done, we also have to run feature extractor and this run evaluation if we want to use the viewer app, because it's based on the features and the decision boundary plot is calculated using that. So Node, feature extractor, and Node run evaluation. We're done, and you can see the accuracy is actually a little bit different, 42.36 compared to what we had previously. So now when we refresh this page, we will see these changing. Maybe here also some of these will look different, I don't know. And of course, some of these samples will not appear here. Let's see. Refresh. So a different result here as expected. And now the decision boundary plot is again pixelated. If you want to have a better one, then you have to wait and put there something like 5,000, or use the one that I provide for you in the resources here. There are two of them. One that you used previously is this KNN50, and the other one is KNN50 after filtering. And they look a little bit different, but not by much. So let's take this one, and in the data models, I'm going to paste it here, delete the small resolution one we just created, and rename this one so that I remove everything except for decision boundary. And refreshing now the page is going to show the other one that I gave you. It's much sharper now. Now if we scroll down, we see that some of these samples are missing. Sometimes entire users might be missing if I flagged all the samples. And I actually flagged all the samples of the flagged users, so those won't appear here anymore. And everything looks fine, but out of proportion. I would like to keep everything the same size here. So I'm going to fix that by going to Styles CSS, at our sample container, and I'm going to add here a max width of 8%. I noticed that this does the trick. So let's refresh, and now the things look better aligned. One more thing is that when we go here at our halfway point where the testing starts, you will notice Prophet here has his data split in two. Some of it will be the training data, and some of it is used for testing. That's just fine. It's where the midpoint happened to be. Now, one more thing I want to do is say somehow that we have this new flagging functionality. So I'm going to added the title here, an info button, and when we hover it, it's going to say some instructions how to use that. We do that in this viewer HTML file, and here in the h1 tag, let me just open it like this and type here span with the class called info button. Let's close this span, and I'm going to add here this info button symbol. And then inside here, I will have a tooltip. Inside it, I will just write. Now let's save this and go inside our styles. At the bottom, one for the info button. Let's make it red and have the cursor be a pointer because we can click on it or hover it. And then when hovering, it's going to make the tooltip text visible. So one more style now for this tooltip text. And I'm gonna have this one have white text on a red background. I think the combination goes well. And let's position it so absolute positioning, hidden by default, and small font size. And let's have it round a bit and give it also padding and remove the bold of the font because that's how they are by default inside of this h1 tag. So refreshing. Here's now our button here. And when we hover it, we get the instructions. So far, we've measured the goodness of our system using one number. But if we want to improve our recognizer, we need to understand what it does good and what not. Like, can it recognize pencils better than houses, for example? A good tool for understanding this is the confusion matrix, a table that says how many items are misclassified as something else. Like here, out of 343 trees, 211 are correctly recognized. But 3 are classified as cars, 1 as a fish, 45 as a house, and so on. Now, let's learn how to code this new visualizer. And don't worry, you won't be confused for long. We will draw the confusion matrix on top of this chart somehow, and there will be a button here to toggle it on or off, so we can still see the chart sometimes. Let's go to Viewer HTML, where we have our chart container, and I'm going to open it up like this and add a container for the confusion matrix here. So this will be a simple div, just like this one, but it will be called confusion container. Let's give this a style, and I will go in styles CSS. Let's look for our chart container and put this one underneath because they're related. And type confusion container. The position will be absolute. And I want it to be far right as possible. So right 0. And let's give this a white background color. And I want a z index of 1. The chart has now there some additional items and I want it to be on top of those. Let's save this and go back to Viewer HTML and add a button to toggle this output as well. So this we will refer to as the output, what is on the right. And now the toggle input function is in JS display.js at the very bottom here. I'm going to copy it and make a similar one for toggle output. And this one is going to use the confusion container instead of this input container. So confusion container here. And we don't need anything else than doing this styling right here. Let's refresh. And here's the button. And when we press it, nothing really happens. But if we open the console here and inspect this element, we can see that this confusion container is actually there. It's just empty, so it has 0, 0 width and height. If we would force it to have here maybe a width of 500 pixels and a height of 500 pixels, then it's now going to cover the chart perfectly. And toggling it seems to work. Let's implement this component next. We will make this component very similar to the chart component here. It's just going to work something like confusion is a new confusion. And here we pass the container the same way that we passed the container for the chart. And then we also need to pass here the testing samples. And we will also need to pass all the classes here. So in order, they are car, fish, house, tree, bicycle, guitar, pencil, clock. And I just realized that we don't have these defined anywhere really. So let's cut this from here and add these to utils. So utils classes. And now here in common utils at the top, we have these styles that contain them somehow, but it's convenient to have them listed as well. So utils classes is equal to what I just copied from there. And back to viewer HTML, I will also pass these options to the confusion matrix component as well. Okay, now we define this confusion in another file. So let's go up here next to the other chart elements. I will also put it inside of the chart folder. So let's put here confusion.js. Inside of the chart here, I will create a new file, confusion.js. And here we begin to type this new class. So class confusion. And in the constructor, the first thing is the container, followed by the samples. We will be passing the testing samples here, and the classes list, and then these options. Let's store these as attributes. So first the samples, then the classes, and I'm going to take out the size and the style from the options. It's really what we need here. Now, the matrix inside there will be an 8x8 matrix, but I will actually make it 9x9 because I want it to include the header section on the top and another kind of header section on the left. Those would have cumulative values on the columns and rows, respectively. So a size for this matrix, let's say n, is going to be equal to the length of the classes, how many classes there are, plus 1. And now imagine the space here divided as a grid of 10 by 10 cells. We'll use the leftmost and the topmost for the labels, and then the matrix will go in the remaining space. So the cell size that we're looking for can be calculated here like so. We need to add another more 1 to that n for it to be proper. We'll display this confusion matrix as a table, so let's create a table element using the create element and passing table here. And now I'm going to pass here a style. We will collapse the borders. Borders make things very confusing to me at least, and we just don't need them. It's going to be quite nice looking without. You'll see. And everything will be also aligned to center all the text elements. And because I want to keep space for those labels on the left and on the top, I'm going to also add here a margin left of the cell size, like so. And the same goes for margin top. Now we also need to append this table to the container. And now this table is going to be the holder of the matrix. We need to prepare the matrix and fill the table. So these are going to be two private methods. Let's get the matrix ready from the samples and then fill the table like so. The matrix will be an attribute here, so we'll have access to it. This prepare matrix function is going to start off with an empty matrix. So let's define it as an empty list like this. But we will have to generate its rows as well, n different rows. Each of them is going to be an empty list. And each row will be filled with n zeros for now. So I'm going to generate this matrix filled with zeros, like so. And now we can start putting here the values coming from the samples. So let's loop through the samples. I'm going to name each sample S because it's shorter, and the next line is going to be quite long. So the matrix of, and now I want to get the index of the true value of that sample. So the index relative to this classes up here. I'm going to type classes index of the true value of the sample, because those are going to be vertically. And because the leftmost column will do something special and have some cumulative values, I want to go past that. So I add here 1. And the second index is going to be the same, but with s.label, which is the label we predicted using our machine learning system. And also the top header means shifting here by 1 as well. We take that value of the matrix at these indices and we increase it. And that's it. Now we just have to return here this matrix, like so. And it will be passed to this attribute. Now the fill table method here is going to add the rows and cells into that table. So let's define it like so. And because I don't want to type this all the time, I'm going to use this destructuring assignment here, and I will take out some of the attributes from this. And now I can just use them by typing them as such. We will loop from 0 to n, like this, and generate a new row in the matrix. This row we generate with the create element, and we use the tr element for table row. And let's append this to the table. And now we can loop again. So now we are going to go through each individual cells and create those. These cells are going to be create element. A TD element is for creating the cells. And let's style this cell so that it has cell size pixels in width. And I'm going to copy this for the height as well. And let's remove the padding also. And now I'm going to add the text of this cell to be the value of the matrix at I and j. Simple as that. We just have to add the cell to the row now, and we can save, refresh, and this looks as expected. These 0 values we'll have to take care of, but I also want to take care of this top text here and the left text here. Let's begin with that. So at the top, after we create this table, I'm going to add to the container 2 more things. So let's generate a div for this top text, like so. And this is going to be saying predicted class, and we'll style it to have an absolute positioning and give it a really large font, extra large. And let's set the top value to 0 pixels, and I'm going to position it 50% from the left, but that's going to position its top left corner 50% from the left. So I'm also going to translate it by -50% horizontally. And let's append this to the container. Now, if I'm going to refresh, it's almost good. I would like it to be lower, like this, if possible. So I'm going to give this a height equal to the cell size, and then I'm going to use flex positioning here to align to center. So let's go here and give the height of cell size in pixels and set the display to flex and the align items center. Okay, much better. But I would like this to be in the middle of this right here. So this should be the middle point. And that means I need to add it a margin of half the cell size to the left. So let's go here and say that. Great. Now we need to do the same for the left text. So let me just copy everything here. And I'm gonna rename this to left text. And the differences are, this is gonna be the label for true class. And I want this text to be rotated by -90 degrees. And here, left and top should be switched. So let's move this top here and this left value here. Now we refresh. Looks good. Let's calculate these cumulative values here by adding everything in this way and everything in that way. I'm going to go after we prepare the matrix here at the end of this prepare matrix. And now we have those values, the ones that we see here in this bottom right corner. And I'm going to use them to add to the 0 values on the left here and at the top. So we do that with a for loop, like so, going through all the elements but skipping the 0th row. And another for loop going through all the elements of each row but skipping the first column, so starting at 1 instead of 0. And here we set the matrix of 0 and j to be increased by matrix of I and j. And the same for the first column also. Let's refresh. And these seem to be just right. This looks like a very small value here, and these all here seem to be small values. None of them is over 100. So I think this calculation is correct. Now, these numbers here is what I would expect to get. These values should match these values here if we would do a perfect prediction. And if a value is bigger, like for example this 466 here is much bigger than this 343, or 537 here, it's much bigger than 339, then we are generating too many of these items. If it's too small, then we are generating too few of these items. So I would actually like to see these at the top as a kind of a relative difference to this. Let's do that also with the for loop going through all of the items at the top. I'm going to modify them now that they exist by subtracting the value at I and 0, basically the value on the left there. Refresh. And now you read these as here we have too many, there is an excess, and here we have too few, there should be more of this item. I think that I would like to see a plus sign there for those particular cases. And also this 0 here is useless and should be removed. So let's do that. I'm going to set here matrix 0, 0 to nothing. And here, if the value is greater than 0, add a plus in front of it. I'm styling these just the way I like. If you want to do it differently, then feel free. But I'm quite happy with what the end result is going to be. You'll see. Okay, good. But we don't really know what these objects are supposed to be. We can probably remember the car, fish, house, tree, bicycle, guitar, pencil, clock, but better if we show the icons and they are part of the styles. So I'm going to go here and style these cells even more, but only if it's the top row and skipping the first item there in that corner. So if I is 0 and j is greater than 0, let's give this cell a background image. And I will set this to a URL coming from this place. So the styles are going to contain for each class the image. And I will take the source of that image and pass it to this URL. Now, here we need to do a j-1 because our j's increase by 1 because of that first column header. And let's close this here, like so. Now I'm going to save this file, refresh, and we should see on the top row what the items are, but these background images repeat now unnecessarily. So let's go here and say background repeat, set it to no repeat. And now let's align these to center, and I also want to give them a little bit spacing from the top there. So let's type here background position 50 from the left and let's say 20 from the... Okay, and let's move now the text lower. So I'm gonna align it vertically to bottom. And let's make it bold as well to be emphasized as a header. Okay, good. And I want to apply the same style also here on this side. So let's just copy this below and replace here I with j and j with I, and here j with I as well. Now this is good. But these values here, the plus and minus, I would like to emphasize them using colors as well. It's hard when looking at so many numbers otherwise. So let's have these positive values red and the negative values blue, kind of like a temperature scale. I'm going to go up here. The color intensity is really going to depend on those values from the left. So we could take out this as a proportion matrix of ij divided by matrix of jy, like so. And let's set the value for red. If p is greater than 0, then I'm just going to take p and multiply it by 255. That's the maximum of the red that you can get. And here 0 red otherwise. And blue is going to be the same, but looking in the negative. And I can't give it a blue intensity that is negative. I have to put here minus p times 255 or 0. And with these, I'm going to set the style color of the cell using this RGB A, like so. Actually, I don't think we need this A at the end, so just RGB. I was thinking to use the alpha as well, but I think that this is going to look just fine. Let's refresh. And you can see some kind of color here. But to get here maximum red or here maximum blue, these differences would need to be really, really big. And they are not. Like, this should be double 339, so 600 something. And even at our current situation with this low accuracy, it doesn't appear so strong. So I'm going to go here and multiply this p value by 2. And that's going to make it more striking when there is a considerable high value here. And this looks good, I think. Now, the next step is going to be to give these cells in the middle a background color, also depending on their value. And I'm going to use linear interpolation here and give them some values in between the minimum value that we see here and the maximum value that we see here. You can also use 0 and the maximum value. It's up to you, really. But let's first take out all of these values from our matrix and find out those extremes. I'm going to go here at the top of fill table and write the values that we're interested in. We take them from the matrix. I'm going to slice the matrix from 1 so that we skip the first row entirely. And then we are going to take just the items inside by slicing from 1 so that we skip also the first element on the left. And I'm going to flatten these so that all of the values are in one long array. And from these, I can easily calculate now the minimum using the math minimum function. I just have to spread this values array like so. And let's do the same here for max using the max function. So now we know the range where we want to do this polar scale in between, and we can calculate the value in between this range using the inverse lerp function, the inverse linear interpolation function that we defined some time ago. I do have a video on that interpolation concept if you want to learn more. But basically here, if we are inside of the matrix so that we're not in the header section, So if these are positive, I'm going to get this p-value using this inverse slurp between minimum and maximum from the matrix of I and j value that we are currently displaying. And I'm going to set the background of the cell here using RGBA. So 255 for red, and let's put 0 and 0 for green and blue. And the alpha is going to be this p-value, which is going to be between 0 and 1, depending on how far it is from between min and max. So this inverse slurp function is a really simple function here. Given an interval a and b and a value inside the interval, it first subtracts from the value a and then divides by this difference. So you get a result between 0 and 1 depending on this difference. Back here, let's save the file and refresh the page. And this is how it looks like. It's really easy to tell what we are seeing here. Like, many houses are classified as clocks, which is a bad thing. But here, many trees are classified as trees. This is a good thing. So one thing that I would still like to emphasize is that anything on this diagonal is a good thing, because it means that the item is classified as itself. And let's change the color for that as the final update here. So let's say if I is equal to j, so if we are on the diagonal, I'm going to have this. Let's copy it. And here, let's close this curly brace, else. I paste this again inside, close the curly brace, and for the diagonal, let's replace here this red, green, blue with 255 and set this one to 0. So this is going to be blue. And again, the transparency is controlled by the same thing. Let's save this and refresh, and we're done with the confusion matrix. And some things here are kind of obvious, like the house could be classified as a clock. I can accept that because we are now just looking at this bounding box there and the aspect ratio, so it doesn't really matter what's inside. But some things here are really strange, like why so many pencils are classified as clocks. This makes no sense. I mean, pencils and clocks look nothing similar, even if you look at the bounding box. Let's close this output and try to figure out what happens here. And if we go here, this is really a mess. I don't see anything useful here with so many things displayed there. What we can do is tell the chart to display fewer items, maybe just the pencils that are labeled as clocks. So these are very easy things to do. We just go to the viewer here, where we have our testing samples that we pass to the chart, and we can filter them. So let's filter these testing samples so that each sample is going to be kept if it is a pencil, but it's labeled as a clock. Now, I'm teaching you this not just for the demonstration now, but also that you can inspect your data like this quite efficiently. And if I refresh here and close this output, all we see now is the pencils. And these are pencils that are within this gray region in our decision boundary plot. So they are labeled as clocks. But now we can click on them. Okay. they are probably all drawn at an angle like this. So that means that the aspect ratio is pretty much comparable to a clock. Most likely, all of these pencils here are drawn at this kind of 45-degree angle. I actually thought that pencils are very easy to classify because they were so clearly visible inside of this magenta region. Let's actually see here. Like if I remove here this filter and refresh, toggle this output, it's like nothing else is there blocking them. But what I understand now, because of this confusion matrix, is that there are actually a lot of pencils there in the middle. We just don't see them because this visualization is so crowded. We could see them if I add my filter back here and remove this part. It's gonna keep just those things that should be pencils. And let's see where they appear now. Pretty much everywhere. And since we are not drawing everything, including Herminio's house, which is somewhere there, it means that our decision boundary plot is scaled in a nicer way. These pencils here seem to have a square aspect ratio inside of this feature space. So far, we've only been using two features, the width and height of the bounding boxes. But we saw that they're not good enough. A pencil like this can be confused with the clock, for example. Today, we'll introduce a new feature, which will measure how elongated the shape is. This will help to separate pencils from other items in a third dimension. Now, Ilya solved this problem on Discord. It was part of homework assignments 3 and 4. So we're going to use his code. And let me briefly explain how it works. He first computes something called a convex hull, the smallest convex polygon that encloses the drawing. He did it using the Graham scan algorithm. It's not the only algorithm that can calculate it, but Ilya used it and I think it's a good choice. It goes like this. First, it only considers the points, not the paths. It finds the lowest point and from there it calculates the angles to all other points and sorts them. Then, in order, new points are added to the stack again and again. But if the points are found to be in a clockwise order, the middle one is removed from the stack. Repeating this until the end gives us the convex hull. Now, Ilya used the edges of the convex hull one by one to construct oriented bounding boxes around the shape, and chooses the one with the minimum area. That's how he solved the problem. Scared? Don't be. Ilya did the hard part, and we're just going to use the end result. I also think that if you study his code, it won't take long before you understand it. We're going to implement the new feature using Ilya's help, who solved homework assignments 3 and 4 pretty much. I'm going to give you this link in the description. Let's copy this code. And I'm also going to write it in a file called geometry.js. Let's go and put it inside of common here, create a new file, geometry.js. And I'm going to paste his code here, format it slightly, and at the top, let's write where this code belongs to originally. And I'm going to paste this link right here as well. And here we find all the functions needed by the algorithm. This returns the lowest point, and it keeps in mind that the y-axis goes downward. Then here the points are sorted relative to their angle. And here is the actual implementation of the Graham scan algorithm. The points are added to this stack right here, and then the stack is returned. There's also this helper function here that calculates the width and height of a box aligned to the hole in some way. These are all vector operations, and they should be clear if you've watched my prerequisite video. But basically, it finds out what is the left, top, right, and bottom, and then calculates the width and height using that. Ilia also returns these vertices here, which were returned back into original space. They're not really needed, I think, but it helps debugging, and you'll see we'll make use of them. Now, this one is basically going to iterate through all the possible orientations and find the box that has the minimum area. And then everything is returned here like so. Two other helper functions here, one for getting the angle and one for calculating the distance. The squared distance actually, because Ilia only needs here the relative distances, and there's no point in taking the square root anymore. It's a kind of an optimization. Now, that's the code pretty much, and it looks good. But how can we be sure it's good? The only way really is to test it. We could write unit tests for it, but I prefer to debug visually. So let's go to our dataset generator file here. And now where we generate the image file here, I'm going to run Ilia's code, take out the vertices from the minimum bounding box. And here we need to pass an object containing points. So I'm going to flatten the paths and just take the points from there and make sure that you pass here this, it's required. And then with these vertices, I'm going to draw them with the red color on the canvas. Now let's save this and open a terminal. Go to the node directory. And here, let's run the dataset generator. Like so. And while it's doing it, we can check the progress here. And we can see now this rotated bounding box. But it's missing one of the lines there. Let me just stop this and fix it by passing the first vertex one more time at the end. So what I will do is I will create here a new array containing all the elements of vertices, and then one more time vertices of 0, the first vertex. Vertex is just a funny word for point. Now if we run this again and check what happens in the images, it's closed as we expect. But I would like to see also the whole, and just to make sure that whatever happens here is correct. So let me close this one more time. And in the geometry, I'm going to go here where the hole is also calculated, and I'm going to add it here. Let's save this file, and back in dataset generator, I'm going to also destructure here the hole that we are passing now, and I'm going to copy this one more time with hole here. And maybe let's put this color to blue. Let's try one more time. Now we can really debug what happens here and make sure that the bounding boxes and the convex holes are what we expect, really. While this is processing, let's go and implement our new feature using Ilia's code. So in feature functions, I'm going to import here at the top geometry. If it's undefined, I'm doing this check because we're going to need to also use this file on the web. And geometry might be there already. And now the feature name is going to be Elongation. And what we do to calculate this elongation is take out the points by flattening the paths. And then we just get the width and height from Ilia's function here. As before. And we return here the maximum between the width and height divided by the minimum of the width and height. And now in practice, it could be possible that the width or height is 0 from the drawings. Like if somebody draws a perfectly horizontal line, then the vertical coordinate is the same for all the points. And then height is going to be 0. And then this is going to be 0. So typically what you can do in this case is wrap these like so, and add the +1 to each of them, because it kind of makes sense if you think about pixels that it does have some kind of height, even if it's 0 from this vector point of view. And it's just one way that we avoid this problem. I'm not really sure if it happens here, but I was thinking about this division by 0. So anyway, this new function now we can add right here, elongation, get the elongation. And for it to work, we need to adapt our distance function in utils right here to use the third dimension as well. So we could do that, for example, like this, by just including here the difference on this third dimension, denoted by this 2 here. So 0, 1, 2 means 1, 2, 3. But it's nicer to write this in a more general way, so we don't have to do this again and again every time we add a new dimension. So let's remove this and initialize a variable called squared distance with 0 and loop through all of the dimensions of the first point one by one and add to this squared distance the difference on that dimension squared. And here we just return the square root of that squared distance, and now we don't have to bother with this function anymore. So let's try to extract these new features now. I'm going to go here and type node feature extractor JS. And now let's run our evaluation. And look at that. We went above the 50% mark. Quite a significant improvement here. Let's see the results on the web as well. So I'm going to go here and make a few changes. In viewer HTML, we need to import also geometry now. And I'm going to do it here under utils. I think it's a good place. And let's save the file and refresh the page. And something is not right because this input shouldn't be there. And if I open the console, I see there are some errors in geometry there, and I'm quite sure they are because this input is empty and it's giving a list of 0 points basically. And let's have a quick look here. inside of geometry.js. There are sometimes used points from the first index, second, third index, at least. So we would need to have at least 3 points for this code to work properly. And we can do that in multiple ways. Maybe we could go here in viewer HTML at the bottom and only update what's on the sketchpad, only process that. For example, if there are paths and if they have more than 3 points. So here I'm writing the opposite and I'm saying return if it's not like that. So this would work here. There's no more error. But the problem is if we do draw something here and then maybe revert everything, it doesn't process anymore this empty page. So I would actually like to return 0 width and 0 height if not enough points. So I don't keep this update here. Instead, I cut it and I go in geometry.js in the function that calculates here the minimum bounding box, and I say paste, but only focusing on the points. And if they are too few, I will return now a width of 0, height of 0, and let's return the vertices and the whole, and I'm just going to return all the points. So points, points, like so. Now this should work again without an error here, right? And if I draw something on the input and I undo, it also changes, so nothing is a car in this model's mind. Now, this is much better accuracy, and also if we look at the column here and the row here, the pencils are doing really, really good now. So we got what we wanted. And let's toggle this output to see the chart as well. And this is quite confusing now because we are having 3 dimensions, so we should plot that elongation also on the 3rd dimension. But it's overkill, I think, and soon we're gonna have even more dimensions than that, and what do we do then? Also, this decision boundary plot, it's not proper at the moment. It should be a decision boundary cube, not a rectangle like this one. But we could start slicing this cube somehow if we really want. Let me first actually remove these samples from here because they are confusing for what I want to show you next. And I do that here in the chart options by typing height samples, set to true. And then for that decision boundary plot, in run evaluation here, I'm going to go at the bottom, and here it's doing the prediction with just 2 dimensions. So we basically get the same as only with the width and height here, because the distance function is implemented based on how many dimensions this point has. So to have a 3-dimensional plot, we need to add another value here. And it would actually require another for loop and passing here another dimension, but this will just be a set of images on top of each other. So we have to slice this cube somehow. And now I'm slicing it at the minimum elongation. And I could slice it in other parts as well if I want, but let's just see what we get here. And I'm going to run this evaluation again. and refresh, toggle the output. And you can see the pencils are actually gone. But that can't be true because pencils are being classified correctly, and they are even classified the best according to our confusion matrix here. What happens is that the slice that we are doing in this cube with the minimum elongation doesn't contain them. We would have to slice further away, maybe with the maximum elongation, since they are the most elongated shapes there. So let's try that. Put here 1 instead, regenerate the decision boundary plot, refresh the page, toggle the output, and everything seems to be pencils. If it's the maximum elongation, our model thinks that everything should be a pencil here. But there must be a place where it kind of contains pencils and something else. So let's try cutting this cube maybe in the middle, regenerate the decision boundary plot, refresh the page, toggle the output, and seems like even here everything is a pencil. Okay, let's go even smaller, maybe 0.2. Refresh the page, toggle the output, and now we see something like that. Basically, the pencils are creeping out somehow and being replaced with something else as we traverse this cube in the z-axis. But let's inspect the samples a bit too. I'm going to go to Viewer HTML and remove this hide samples. Let's comment it for now. And here, let's still focus on the pencils, but only those pencils that are incorrectly predicted. Let's refresh, toggle the output. And here are the incorrectly predicted pencils. But this decision boundary plot now is kind of useless because we don't really understand it anymore with the third dimension there. Like, these are all wrongly classified pencils, but some of them appear to be over this magenta patch here because they might be in somewhere close to low elongation. So if I would click something here, you can see this pencil is very fat, so to speak. So it's in that zone where there was no magenta at all, maybe. And that's why it's categorized as a house and not a pencil. This seems to be a guitar. It's also a little bit thicker. And all of these bounding boxes and convex halls look great, I think. Really good job, Ilya. What happens here? This looks interesting. This looks like a problem, but what I think is here is that there is actually a small point there that somebody drew. And in our system, if somebody makes a point, it's not going to be drawn because there is no thickness, basically. But it might be there. Let's inspect a little bit. So it's this 5078 image. I'm going to go in our data set JSON this time, and 5078 is here. Let me format this. And I actually see here the first path even. It's exactly the same point repeated twice. So I guess this can happen too. Basically, there's one path there that is small and it's not rendered by our software, but the calculations pick it up. So it's not really a problem with Ilya's implementation. Maybe it's a problem with mine, with my visualization, but I don't want to bother with things like this. So let's forget it's an issue. Let's focus on clocks next. Most clocks are round, so the next feature we'll implement is a kind of roundness measurement. I've already done something like this in my AR portal drawing game tutorial here on YouTube, so you may know it already, but this time we combine it with the convex hull from before. To measure the roundness, we first calculate the length and the area of this shape, and compare it to the area of a circle with the same length. If you want to learn why the circle has the largest area, I have a video on that. It's quite intuitive though, so I don't think you really have to watch it. Now, get ready for another round. To calculate the roundness, I'm gonna add some functions here inside of the geometry file. Let's begin with the function called length of a given polygon. Now, this polygon is just going to be our paths, but I write it here as such because I think it gives the idea that the function will consider the first point also at the end to loop. And let's implement it like so. Initialize the length with 0, and then loop through the points like so. And get a value for the next index. So next index is going to be I plus 1, but when we are going to have I is equal to polygon length minus 1 at the end, adding 1 to that will give us an index that is not good. And we should loop that around to be 0 again. So I'm going to use the modulo operator like this. And add to the length the distance between the polygon of I and the polygon of next I, like so. Let's return now this length, and because we're using utils here, I need to add it here at the top to include it. If it's not existing, then include it like that. And we are adapting now this file from Ilya here, so let me just write a quick comment here, adapted from the original author. Now, the next thing we'll need here is to calculate the area of a polygon. And we'll do that by breaking it into triangles according to some fixed point and calculating the area of each triangle and adding them together. So let's say our fixed point is going to be A, and that will be polygon of 0. And now we loop from I is equal to 1 and less than polygon length minus 1 this time, because we're also going to use this next index here, but we don't want to loop anymore. And here, let's define B as the polygon of I and C as the polygon of I plus 1. So A is going to be fixed, but B, C is going to change from those next to I, and then B is going to be the previous C, and we get a new C, and so on until we add up all the triangle areas. And for the triangle area, I'm going to write a separate function here called triangle area between these 3 points. And let's return the area here. To get the area of a triangle, we're going to first calculate its side lengths and then use Heron's formula. It's one of my favorite formulas I learned in school. Now, I won't prove it here, but you can take it as a homework and prove it yourself, maybe using the Pythagorean theorem. Anyway, this way of measuring the area of a polygon is not the only way. In fact, in the portal drawing game I mentioned earlier, I used the shoelace formula, and that one works with concave polygons as well. Check it out if interested. So the formula works by calculating the lengths of the triangles. So typically we refer to as the side length of A, of B and C. And we do the same thing here for B, and that will be A and C, and we get here C, and that will be A and B. So these are the side lengths that we just calculate as the distance between those. And then we define P as the semi-parameter or half parameter, the half length of the triangle. So this is going to be A plus B plus C divided by 2. And this is Heron's formula. So the area will be the square root of the half parameter times P minus A times P minus B times P minus C. We just need to return it here. And now we can use these two functions, the area of the polygon and the length of the polygon, to implement our roundness function. The roundness function is going to take the polygon as a parameter, and first thing we do is get its length and area using the functions we built previously. And now let's calculate the radius of the maximum circle that could be built using this length. So that would be the length divided by 2 pi, like this. And the area of such a circle would be pi times the radius squared. So the roundness is going to be the area divided by this circle area. And here we could return the roundness, but in case this circle area ends up being 0, then this roundness is going to be not a number. So to be safe, we are going to check here. If it's not a number, let's just return 0 in that case. Otherwise, we return this roundness value. And that's it. Now let's debug if what we implemented works. I'm going to go here in dataset generator, where we were previously drawing these vertices and the hole, to debug Elias code. And let's include now our roundness calculation here. So we can do that like this. Roundness is equal to calling geometry.roundness on the hole this time, because that's what we want to measure the roundness of. And now I won't need these vertices anymore. I will just focus on the hole here, but I will give it a different color. The color will range between blue and red. If it's blue, it means a low roundness, and if it's red, it means a high roundness. So let me go here and say R for red is going to be the floor of this roundness, multiplied by 255, because that's the range of the colors. Then green is going to be 0. We won't care about that. And for blue, I'm just going to copy this and invert it here. So 1 minus this roundness multiplied by that. And this is B here. With these, we create a new color. And I'm using here these template literals and replacing the color here when drawing the hole. Now let's save this and open a terminal and regenerate the data. And let's check it out as it's doing it here in the datasets image. This looks reddish. Okay. Okay, much red here in this house. Pencil is quite blue here. And the clock is red, as expected. Let's go here and make this line thicker. I'm going to add here 10 pixels in width, and I will modify this draw path function from here to accept also the width. Let's set it by default to 3 and replace the 3 that was hard-coded here previously. And let's write a function for extracting this roundness feature as well. I'm going to go in feature functions and type it here. It will be get roundness of the paths. And let me copy here this code from the elongation, because we're going to call Ilia's minimum bounding box function. And instead of width and height, we are going to extract the whole now, and then return here the roundness of that whole, like so. Let's add this also to our feature list here. And roundness, get roundness, and regenerate the data. Extract the features. And run our evaluation. And look at that. We're getting above 60% now. But this decision boundary won't be proper there because it's not yet slicing the hypercube, the 4-dimensional cube now, just yet. We'll get to that. But first, let's just refresh the page. And our colors here are not proper because they are inverted by Ninja Coder's new style here. Let me just go back here in dataset generator and invert these as well. So 255 minus that, 255 minus that, 255 minus that, and rerun everything. In the features, and run the evaluation. Forgot that hypercube again, but we'll get to that. Okay, so refresh. And now it's how I want it, red for these. You can see a lot of clocks are red, but there is a lot of red everywhere because things tend to have a high roundness value. If you look at the convex hull here in general, if you would like to differentiate better between really round things like these circles here that are making the clocks, you could use a nonlinear function here for the roundness, like maybe square this value, or even a higher power will make the difference even more significant, maybe like 5th power here. You'll notice that generating these decision boundary plots is becoming slower and slower because the classification is becoming slower and slower because we're adding more and more dimensions, so that distance function has to do more work for all of the neighbors repeated many, many times. Let's refresh. And now these differences are more striking. The circles here do appear more reddish than anything else. But our decision boundary plot still looks the same as before here. And that's because in our run evaluation here, we are still sending 3 dimensions to it when we now have 4. And we could, in principle, add one more point here, but to make this function general enough so that we don't have to do this every time, we can just remove this and use a while loop until the length of this point is going to be the number of dimensions. Let's just add the value here. So maybe point push, and I'm just going to slice at the lowest value in the elongation and the roundness dimensions and get something. But this is not really going to be something useful when we have so many dimensions. So this decision boundary plot is only useful for 2 dimensions, really. Let's see what we get. We just have to run the evaluation now so that we get a different decision boundary plot. And refresh the page, toggle the output, and that's how it looks like, apparently. Not interesting, really. Let's go back to the confusion matrix here and notice how white this section is becoming here and how good our system became at recognizing pencils and clocks, which is what we were trying to do. Looking at elongated shapes and looking at round shapes started working now. What doesn't work is the car being confused with fish and the fish being confused with the car. We have this small square here. And actually, cars are also confused with bicycles and fish the same, because these tend to have the same aspect ratio. And their convex holes tend to look similar as well. The guitar as well actually gets confused with the car and the fish for similar reasons, I think. We just didn't try to extract features that would help distinguish these. And we could, like cars are much more blocky, I think, and fish are much more organic in shape. Maybe looking at this kind of a curviness, how curvy the lines are, it may help to recognize the fish and distinguish them from cars, also from bicycles. The bicycles, well, they do have circles here, so maybe using the roundness measure in some other way could help to recognize those. Maybe looking for corners. When I look at houses, they typically have some triangles there, corners, many corners. There is a problem when considering triangles, and let me show you. Let's close this and start our input here. If I'm going to draw a house, I could draw it, for example, like this, and now start making a rectangle here and a triangle here, like so. And these could be recognized relatively easy if you look at the data that we collected, because they are 3 independent shapes, so you could maybe recognize that one is a triangle, one is a rectangle, and there is a flat line here. But what if you draw the house like this? Now, the second shape will be just this kind of upside down U shape. And then the roof, I'm not going to draw a full triangle, I'm just going to draw this upside down V shape. To me, both of them look pretty much the same, but the data that we store is significantly different. This has just 2 sides, this has 3, this has 3 sides, this has 4, and you can draw these in different ways. But the problem is, if we would like to extract things like triangles or rectangles or these kind of shapes, looking at the vector data is not as easy as looking at the pixel data. So we're going to study how to access pixels next. So far, we've been working with the data in raw vector form, the coordinates of the points and the paths they create. But that's not what we humans see when we look at the drawings. We see the pixels. And some features can be calculated more meaningful if using those. Like, these drawings look the same, but their vector representation is very different. And it would be quite strange if they would not be classified as the same thing, wouldn't it? If you've never worked with images, you can watch this video where Green Radu explains how to make an image recognizer that works with the camera. I think it's a good watch, especially now that you have a good understanding of machine learning already. Now, I won't teach you any sophisticated image processing techniques, but I want to set you up just in case you want to experiment more. There are a bunch of things that can be tried out with this new approach. Self-study them, ask me questions in the comments or on Discord, and we'll try to figure things out. Let me show you how we can access the pixels from the canvas. I'm going to do this in the console here and type sketchpad CTX, getting the context of this sketchpad that we're drawing on, and get image data from 0, 0, which is the top left corner, using the sketchpad canvas width and the sketchpad canvas height. So I want to get all of this information. And if we press enter, we get this, which is containing some information about the color space, the width and height, 400 by 400, and this really, really long data array here. Now, this data array is going to be filled with the zeros pretty much, because that's what is drawn on the canvas now. Everything is actually transparent black. This stands for red, green, blue, alpha of the first pixel in the top left corner on the canvas. And this is the pixel on the right of that. So red, green, blue, alpha, red, green, blue, alpha, and so on. If I'm going to draw a line here on the canvas and run the same code here again, you can see zeros here, but at some point we start getting some values. And these are the values from this line that I drew here. And they only appear as alpha values because the lines are black, actually. They are here inverted because of the styling. But basically, anything with an alpha is a pixel that is lighting up. So that's what we want to extract from here, really. We don't care about colors. We just want to know which pixels are visible and which not. So if I'm gonna bring this code back here again, we can filter this to take just the fourth item in the array. Every fourth item in the array using filter on the data and taking the value and the index. So here we're gonna filter using this index if modulo 4 is equal to 3. And this gives us that, just the alpha values, and they are 160,000, so this is 400 times 400. A matrix written in linear form, pretty much. So let me close this console and write the code to extract these pixels in our feature functions. I'm going to go in Common, Feature Functions, and here below the roundness feature, I'm going to implement a function to get these pixels. It won't be a single number as an output, it will be all the pixels. It's not a feature yet, but eventually we'll use it as a feature as well, you'll see. And I'm gonna write it here in the feature functions for now. So let's write here get pixels, and given the paths. Now, by default, we used this 400 by 400 pixel canvas all the time. I'm going to set the size here equal to 400, but we can set a parameter here to get the pixels from a smaller canvas if necessary. Let's first define our canvas, and I'm using let here and setting it to null because now I'm going to do a trick. I'm going to try to initialize the canvas for the web by asking the document to create a canvas element like this, and then setting its width to the size and its height to the size, like so. But if this fails, it probably means that we are doing this in a node, and I'm going to catch an error. I'm not going to worry too much about what the error is, because in our environment, this can only be the reason why it doesn't work, that we're trying it on node. So this code here is for node, and here we have to require the create canvas function from node modules canvas, where the canvas was installed. And then our canvas can be initialized with create canvas size and size, like this. Now the code should work both on web and inside of Node. And we can now get a reference to the canvas context, like so, and draw these given paths here on this new canvas. We then get the image data. From the whole canvas, and take out just the alpha values that we're interested in. So I'm just going to return directly image data dot filter value index, and then index modulo 4 when it's equal to 3. So every fourth element will be returned. Now we're drawing here, and we haven't included that file here yet, so I'm just going to do that real quick. Draw, like so. And now let's test our code in the dataset generator again. I'm going to go here in Node dataset generator, and we need to include the feature functions here. So feature functions and feature functions. And let's go down where we are generating the image. And we don't need this fancy stuff anymore, because this new visualization will be just me writing some text on the images, how many pixels are visible. So let's first access these pixels using our newly created function, and let's store the number of pixels in a variable which we're going to call complexity, because I'm eventually going to make a feature from this, and complexity just means the more pixels, the more complex it is. So let's say complexity is, and we count now how many values are non-zero. These are just the alpha values, remember that. So if they are visible, they will be counted. And then let's just draw some text, this complexity value, and let's use blue color. Now this draw text doesn't exist, so let's save this file and go here to draw.js. We can draw paths, but we can't draw text just yet. So we need to implement a function for this, given the context and the text. And the color, we set it to blue, but let's give this one a default color as well. And now the location by default will be 0, 0, where we want the text to be in the top left corner. And let's set a relatively large size, because we are just printing there those small thumbnails in the viewer. The text should be quite big. Now, this function is going to first set the font, and I want it bold. Let's concatenate here the size, and I will use Courier font. Because I want the text to be in the screen, I want the baseline to be on the top, because if 0, 0 coordinate is used, otherwise the text would just be over that and we wouldn't see it. And I'm going to put here text baseline stop. And let's set the fill style to the color and fill the text at this location. I'm just spreading the array into the two X and Y components. And that's it. Let's save this and open a terminal. Make sure we are in the node folder. And let's generate our dataset once again. And while it's doing that, we can quickly check what happens here in dataset image. And this is a number that probably works, meaning it's the number of visible pixels here. Maybe it's okay, we'll see later when we can visualize them in the app. But while it's doing this, I'm actually going to implement the complexity function that I mentioned. So let's go to our feature functions here below the new function we just created. And the complexity function is going to be just get complexity from the paths, and it's going to return this one number. So first thing that happens is we extract these pixels. And now we're going to count how many of them are visible. Like so. And we can add this new feature here. And get complexity like so. Now we're dealing with this 5-dimensional feature vector. And I don't really know how good this feature is going to be. I don't really have high hopes. I just want to teach you how to work with pixels. And then it's up to you. You can look online, find some help how to do image processing if you're curious, but I won't get into that. Now this is done. Let's also extract the features. And this is probably going to take some time now because doing this pixel manipulation is time consuming. Each image is 400 times 400, so a lot of calculations. Let's add here also this kind of progress indicator. So I'm going to go to feature extractor, and this for loop here where we are looping through the samples, let's rewrite it using a classical for loop, looping through all the samples like that. And let's here initialize the sample as the samples of I. And at the bottom here, let's print the progress using our utility function I and samples length -1 for 100%. Now, next time we run this code, we will know how long it takes. At the moment, I have no idea, so I just have to be patient. And it's done. Let's now run the evaluation. There is some improvement. It jumped to 66.13 here. And now this decision boundary plot is going to use all of the features because we implemented in a general way last time. But I don't really care about this decision boundary plot anymore. It's not very usable as it is when more than 2 dimensions. So we're done. Let's refresh the page. And this is what we get. We see now the numbers here. And I think they're proper. This is a very small value here, 1,000 something, when most of them have several thousand, and you can see just a few pixels showing up for this small pencil. I think that this is correct. But thinking about it, it's kind of unfair to say that this is less complex than this, because they kind of look the same. If we talk about the feature meaning complexity, maybe we should scale these items so they fill the whole canvas and then count how many pixels are lighting up. Let's try to do that. I'm gonna teach you a little bit of image processing anyway. So let's just scale these and stretch them to fill the whole canvas and see if this feature improves or not. But I won't insist more than that. In feature functions, where we extract our pixels here, I'm going to pass another parameter to the function saying if we want to expand or not, so that the drawn image fills the entire canvas. And if it's set to true, which will be the case by default, then we go here before drawing the paths and rescale these paths somehow. We check if we need to expand, and if we do, I'm going to take the bounds first, the minimum, maximum on the X and Y. So let's take out the points by flattening the paths. And these bounds will be an object with left equal to the minimum point, only looking at this X coordinates, the first coordinate here. So I'm going to copy this like so for the right with the maximum here. And let's copy both of these for the top and the bottom. Now, these will be 1 here because we're using the second dimension. We are now going to remap these points and generate some new paths with remapped points. So let's write here new paths, and this is going to be an empty array. And we're going to loop through the paths, path by path. And now we're going to generate new points from the path's current points. So these will be in this variable, and we'll use the map function where we remap each point P to be a new two-dimensional array. The first will be remapping using inverse slurp between left and right using P of 0. And this is going to give us a value between 0 and 1, depending how far from left to right we are. So we have to scale this also by the size of our canvas. Now I'm going to copy this again here, and this will be between top and bottom using the first dimension here. Now we need to push these new points into our new paths every time we create them. And finally, we can draw here the new paths on the canvas. So new paths, like so. And this will go in the else clause. So here we have else. We do that because in this case, we don't want to expand anything. Now, if we open our terminal and regenerate our data, if we look here, we will start to see that the values are different than before. But I would also like to visualize what we did exactly. So while it's running, I'm going to redo the visualization part in this dataset generator here. And I'm going to show the new image that we get after expanding them. So here, after we have our pixels, I'm going to figure out the size. They are going to be a square canvas always. So I just take the square root of these pixels, length, And then let's get the image data that we have on the canvas at the moment. I just need the data structure, essentially. And I'm going to loop through these pixels one by one, and I'm going to write on top of this image data the values that we currently have. So to do that, I'm going to consider just this alpha value. Others will be 0 for red, green, and blue. So starting at the ith times 4 index, because they come in group of 4, I'm going to set the image data at the start index to 0. So this is for red now, and this has to be copied 3 more times here. And now we're going to set the green and the blue and the alpha component. This is not 0. This will be the alpha that we calculated previously. And now we put this new image data on the context. So put image data 0, 0. And I don't think I need this complexity value appearing anywhere here when debugging. I know the number of pixels is calculated correctly already. Let's regenerate the data. Okay, this is done. And now let's extract the features. We can see how this progress indicator works now. Much slower when we're dealing with these pixel values. Okay, and now let's run the evaluation. And done. A little bit improvement from previously, but not much. And this is what we get. The images are now stretching all over the canvas there. And I kind of like this view because now we can see the drawings much better, even for those who made small images. They are stretched here like that, but remember that all we do with these stretched images here are counting the pixels as a kind of complexity measure. All the other calculations still happen the same on the raw point data. One thing I am really curious to see is Herminio's house. Aha. It was like that. For some reason, the app registered some point very, very far away, and that's why its width is so huge. Now let's try drawing here, and I do sense a little bit slower reaction time here, because every time we make a new update to the drawing, it's going to take the features, including this pixel feature, which is slower to calculate, and basically it takes a little bit longer time here. I would say it's still real time. We move on to neural networks next, and I don't have the patience to teach you what they are, but don't worry, I know just a person to do it. Take it away, Red Radu.
Neural networks are computing systems inspired by the biological neural networks in our brain.
These are some neurons.
These branch-like structures receive the signals. When stimulated enough, a neuron will fire a signal through its axon. So a single neuron does something really simple, and intelligence only comes when they work as a team. You see, your brain has 86 billion neurons. You also have quite many of them in your spinal cord and sensory organs, like in your eyes and ears. These sensors send signal to some neurons that pass it to the brain. There, the processing happens like a chain reaction where some neurons fire, some don't, eventually signals arriving to motor neurons that pass them through your spinal cord and make some muscles contract in very specific ways. Hey! A lot happened in just a split second. Let me try to slow this down and explain it to you. Pay attention. Sensors inside the ear pick up compression waves from the air and send signals to the brain, which figures out the direction based on different intensities. Signals then travel to neck muscles, tell them to contract and turn the head in that direction. The eye catches a glimpse of what's happening, and new signals travel to the brain. Peripheral vision is blurry, but good enough information exists to detect some kind of object approaching, and new signals travel to facial muscles to contract and protect the eyes from getting hurt. Eyes are really important. At the same time, the brain begins a kind of defense protocol by sending signals throughout the body. Time passes and the image becomes more clear. The brain does pattern matching and recognizes the object as a ball. Contextual and historical information will play an important role in what happens next. Let's stick to the first one. The brain concludes there is no threat and uses knowledge about physics it learned during its lifetime to predict where the object is headed. It then sends new signals to the muscles to contract in slightly different ways to catch the object instead of blocking it. And the rest is history. One history where the brain did a good thing and not much happens afterwards. But sometimes this happens, and the brain learns it did something wrong and configures itself so the same thing doesn't happen again. Hopefully. Anyway, I'm feeling really good about myself now that I know my brain can do something like that in an instant. Hope you do too. Our car's neural network will do something like that. Neurons on the first layer will be connected to the sensors. They will send signals forward a few times. And the last layer will be connected to the car controls to make it actually do something. Spoiler alert, we'll be working with relatively small networks here. But that's okay, because we actually don't need very large networks to solve this problem.
Now that you have a basic idea, take the code from the link in the description. You'll need it to follow along. But beware, I will just briefly go through it. And if you really want to understand it, go watch these 2 videos first. Of course, watching the whole self-driving car series is even better. There is one thing about what Red Radu said in the beginning that bugs me.
So a single neuron does something really simple.
I got this comment from Mikhail, and I should point out that biology is really not that simple. We don't fully understand how brains work to this day. But a simple model like that is all we need to build an artificial neural network. I definitely don't want you to draw the wrong conclusion, and that comment made me think twice about my wording. I've added the 2 files here. In common, we have network.js now, and in web.js, we also have viewer.js here. Viewer.js is pretty much the same as in that tutorial, except that I made these output labels be images now. There I used emojis, but here I wanted to use the colored emojis we generated earlier. And there are a few other small tweaks here and there, but pretty much the same code as you've seen there. And network.js here is the same code from the tutorial with this small difference here instead of how it was originally written. Because in the self-driving car case, the car could press 2 keys at the same time, like maybe accelerate and go to the left. But here we need to decide which is going to be the winning class. So we are leaving these outputs as the raw value there. And we will select the class to be the maximum value that we get. I've also added here this export so that it fits with our current structure. But other than that, it's exactly the same. We have here the neural network made out of different levels, the level having inputs, outputs, biases, and the weights. We have methods for randomizing these weights and biases because that's how we knew to optimize in that other course. We just tried randomly different networks and hoped for the best. We kept the best one all the time. Then the feed-forward algorithm just implements that summation and outputs all the outputs. the feed forward for the whole network just feed forwards each individual level like that. And the only difference is really this line of code here. But if you've watched that tutorial, you know what it means. Now, to use this new code, we will build a new classifier next to our KNN classifier that we had here already. And I'm going to copy this one for reference. Let's copy and paste it here with a new name. I will rename this file mlp.js. MLP stands for Multi-Layer Perceptron. And I think it's a good name here because neural network is kind of like NN from here, so I want to keep this different, and it will also match with what we do in Python later on. Now we will modify this code inside of mlp.js. So here we have MLP now, and let's export here also MLP, like so. And I'm going to empty here the constructor. We won't save the samples here. This model doesn't store the samples. It's what makes it much more efficient than this k-nearest neighbor. Let's remove them from here as well. And I'm going to empty also this predict method, but I will keep the return so that we know what structure we need to return things in. Now, the constructor is going to take as parameters the neuron counts. We need to know how many neurons we should use, and also the classes. The model needs to know what are the options. Let's save these here as attributes of this MLP. So the classes. And now let's initialize a neural network with the code from the file we just added and pass here the neuron counts. So this we need to include here, same as we include utils, but here we include the neural network, like so, from the network.js file. And the prediction here is what changes. We just get the output from the neural network's feed-forward algorithm when we pass this point, the parameter from here, and this network that is stored as the attribute of the class right here. From these outputs, we calculate the maximum. So let me use math, max, and spread here, this output array. And let's get the index of the element with the maximum, like so. And the label of that is going to be taken from classes at that index. Simple as that. Now, for consistency with the KNN, I will keep here an object with the attribute label, but we don't have any nearest samples here. It's gonna be null. Let's save this file, and to evaluate this MLP model, I'm going to copy here in Node the run evaluation. So let's copy this, paste it here, and we will have two run evaluations. One will be with KNN, and the other one will be with MLP, like so. So let's modify this run evaluation MLP. And the first thing we do here at the top is rename our classifier to MLP, like that. And then reading it here from MLP.js. And here where we initialize our model, we don't have KNN. Instead, we have MLP. And this MLP is going to take the two parameters. First, the neuron counts. And we have 5 features at the moment. So the first neuron count is going to be 5. And the second one is going to be, let's just say, directly the outputs. And we have 8 different outputs. The car, fish, house, tree, bicycle, guitar, pencil, clock. And the second parameter we pass are the classes, which are here. And these hard-coded values, we don't have to keep them hard-coded. We can just replace here 5 with taking the training sample's first item there, the point, and the length of that point. And here is just the length of these classes. So now we don't have to change these anymore. They will work as expected. So this is a neural network without a hidden layer. It just connects the inputs to the outputs directly. And we will experiment with hidden layers later here. You could pass a hidden layer with maybe 10 neurons and another one with 10 neurons and one with 5 and so on. But at the moment, we don't. We just have this simple connection. Now let's copy this and replace every time we want to do a prediction KNN with MLP, and here also. That's it. Now let's run this new evaluation. I'm going to start the terminal, make sure we're in the node directory, and node run evaluation MLP this time. And it's really fast. I didn't speed up the video this time. It's also not very good. This accuracy here is random chance. If you've done homework 7, then you know this is random chance. And Leo Caesar 3D mentioned this in a comment. Now, because this is based on randomness when we add the weights and biases, every time we run this evaluation, we will get a different value here. Sometimes we're more lucky than others because the networks that we are getting just happen by chance to be a good or a bad configuration. In the self-driving car course, we experimented with many different networks and choosing the best. So let's try to do that here as well. We will try to fit the network to the training data. So let's open our MLP file here and implement a new method here called fit. The samples, now we pass the samples to this because it's going to need them, but it's not going to store them. It's just going to update the weights and biases according to these samples somehow. You'll see. And we'll use the same strategy of randomness and trial and error. We will try, for example, 1,000 times and keep the best network that came. So let's consider the best network being the one in the class attributes, and the best accuracy, let's evaluate that network on the samples. Now we are evaluating on the training data. We are not yet seeing testing data, but we're trying to improve the model. This is okay. I'm going to now loop through this number of tries, and let's try to generate a new network. After we do that, we evaluate its accuracy on the training samples. And if it's better than the best accuracy, we keep it. And we also keep the network like so. Now here at the end, we just set this network to the best one that we found. And we still need to implement this evaluate method here. It's not complicated. All we have to do is implement the method like that and count how many of them are correctly predicted when we loop through all of the samples, take out the label, and remember here to destructure because that's what MLP predict will return on the sample point. Now, the true value for this is what is stored in the sample label. We know the true labels for our samples. But if this predicted label here matches the truth, then we increase the correct count. So correct count increases if truth is equal to label 1, otherwise it doesn't increase. And here we just calculate the accuracy by dividing correct count by samples length. And let's return this accuracy. Let's save this file, and in run evaluation MLP, after we initialize the MLP classifier here, we fit it to the training data. So MLP fit training samples. And let's try this again. I'm going to open now the terminal and rerun the evaluation MLP. Now we get 26.8, which is much better than the random chance things we were getting previously. So it is working. We are searching through 1,000 networks. And if we're going to increase here maybe by, 5,000, then this accuracy should be even better, because now it's trying even harder. It's going through even more. It's an expectation, but of course you can be really unlucky with those 5,000 randomly generated networks, and then it's not going to look so good. And it doesn't really make sense once we have found a good one like this to go back down to a crappier one. So what we could do is save this model every time we find it, and then load it when we do this optimization, so we can continue a previously made optimization with the saved network as a basis. Let's save this model. So I'm going to type here write file sync, and we will need the constant for where the model should go. And then I'm just going to stringify the whole MLP object, and that's it. Now, I want this model to be accessed also by the web page so that we can try the neural network there as well. And I'm going to use the same structure here, putting model.js also as a constant, and here initializing a variable called model, and then putting this stringified JSON inside of it. And now let's close this template literal, like so. Now these constants need to be added. I'm going to go here in constants.js, and let's copy this one for the decision boundary. This is going to be model now, and it's going to be in this models directory. Let's call it model.json. And the JS object, let's just copy this min-max here. And this is going to be model.js and model.js. Now, when we are going to run this evaluation, this model with 31.96% accuracy is going to be saved in data models model here next to the decision boundary. And if I'm going to format it, you will see it has the neuron counts information, the classes information, and the network with all the levels, which is just one level for this one. And we have the inputs, the 5 different features, the outputs, the result of the feed-forward algorithm, and here the biases and the weights from all the inputs to all the outputs. Now, the inputs here and the outputs here are just the last values that have been used in the training process. They are meaningless. Every time you do a classification, these will become overwritten with whatever the features are, and these here are going to become generated from the feed-forward algorithm. They're now just placeholders here, and that's okay. Now, if we want not to lose this model and get at least 31.96% accuracy in the next model, we have to load this one. So in Run Evaluation MLP, after we do this initialization, let's load it from that file before we do the fitting. So let's say here, if that file exists, the one that contains the model, I'm going to mlp.load and parse it after we read it. Like so. Now this load is a really simple method that we still need to implement here inside of MLP.js. I'm going to do it just below the constructor here and load. Given an MLP model, I'm just going to update this model's neuron count to that one's. And the same thing for the classes. And the same thing for this network. It's basically a copy constructor. Now let's save this and rerun the evaluation. And the same accuracy as before. We didn't get lucky with the 5,000 tries here, but if we try again, still no luck. If we try again, still nothing. Still nothing. But now it worked. So we could optimize like this. It would take quite a long time to reach the same level accuracies that we are getting with our KNN. There are better optimizers than this trial and error out there, and we'll try those later. But now let's get this to work on the web page as well. Let me close some of these things. And here in Viewer HTML, we are going to have to import many JavaScript files. So here we need the new MLP classifier, similar to the KNN classifier. Then we also need that model, the one that we calculated on the back end. So this is here in JS Objects, the JavaScript variant. Then we need the neural network code and the visualizer. Let me add this network.js here underneath utils and the visualizer here from this JS folder. Now we'll visualize this on another canvas, and I'm going to define it here inside of the chart container underneath the confusion container. So this is going to be network canvas, and it's going to be what we draw the canvas on. Let's give this a style similar to the confusion container. Inside of styles CSS, the confusion container is here. I'm just going to copy it below, rename this to network canvas, and give it a black background. Let's save this, close this file, and let's begin to work with the MLP classifier. We won't use KNN anymore in this course. I'm going to keep it here for reference, but I'm going to start using the MLP classifier. So MLP, and I will initialize it with empty and empty here for the neuron counts and for the classes, because they will be loaded from the model that we have calculated with the scripts. Now, every time we see K and N here, I'm going to comment out the line and write MLP variant below. So this happens here when we are calculating the accuracy of the testing samples, but also below for the real-time processing here. So let's copy this, comment it out, and replace KNN with MLP. So it's the same thing, but now with a different classifier. This should work already, but we are not visualizing it yet. So let me go here at the top and also do the visualization. I'm going to set the width of the network canvas to 500 and same for the height. And let's get a reference to the network context from this network canvas, like so. Now, we also need the output labels to look nice, and we can get those here after the graphics generate images. But let me just put this maybe here above the sketchpad and below the confusion, because now we have these related somehow. So we generate these output labels from the styles by looking at the values of the styles and then remapping them so we only take out the image of that style. We don't care about the color or the text, just the image component. And then we use our visualizer to draw the network on this network canvas, the network stored in our MLP classifier, and using these output labels that we just defined. We also want to update the visualization here after we do a real-time prediction, like so. And now let's save the file and we should be able to test. Refresh the page. And something looks horribly wrong. I noticed that this width and height features that we calculate for this empty canvas are -infinity and -infinity. And this is causing some problems now for this neural network. It was working okay for the KNN because it was just some coordinate. But now it's into some calculations there and it's causing some not a number to happen and problems. So let's fix those functions real quick. I knew they will become an issue at some point. So inside of this feature functions, at the top, our width here, if the points are empty, if there's nothing there, I'm just going to return 0 for the width. And same thing will happen for the height as well. Now let's refresh this page and close this console, toggle the input, and now the network does something here. It's saying that this is a car because this car node here, output value, it's the highest, and you can see that as a yellow color coding here. Blue means negative values, and the least visible they are closer towards 0. So this is very visible, bright yellow here. It means it's a high value. And it's not fantastic. 33.28%. We had much better results. But it is what we can do now with this random optimization strategy. And these here at the bottom are the features. So when we look at this, we can see a relatively high value for the width because it's a wide image. And this is the height here, which is smaller. Then this is going to be the elongation. apparently quite a small value. But if we draw something like this, a really elongated shape, it's going to be bright. And then these final ones are the roundness value, and this is not round at all. But if we do make it round, it's going to be bright. And the last one is the number of pixels, basically. So if we would fill this space with a lot of pixels, then that one starts to light up as well. And apparently it is able to pick up that this is a clock. One thing that I still want to do is toggle the output, and this doesn't work anymore. We need to rewrite it so that we consider this one as well, not just the confusion matrix and the chart. So let me go to display.js and quickly rewrite this from scratch. And I will just say that if the network canvas is visible, then let's make this one invisible, and let's make the confusion container visible. Otherwise, if the confusion container is visible, we will make it invisible. Otherwise, we will make both of them visible again. So now we are going to toggle between the three items there. Let's save this, refresh, and this seems to work. Interestingly, we get a lot of zeros here. So it looks like the network that we have is really good at recognizing cars and pencils and clocks, but nothing else. So now we can see that this accuracy really doesn't tell a good story, but this confusion matrix really tells us what is really going on. The model forgot about these other things pretty much. And let's see now in this decision boundary plot. We can't really see much because it's still this high dimensional cube. But we could revert to the simple features. I like doing that. Let's go back to width and height, 2 features, and see how this decision boundary plot looks like now when using a neural network. So in feature functions, I'm just going to comment out here everything except for these width and height. And let's open the terminal and let's rerun the feature extraction. So node feature extractor.js. And now it's fast because it's not doing the pixels thing. And now we have to optimize again our neural network model. But the model that we created previously here inside of the data models is pretty good, and it's using the 5 different features. So it's incompatible with the 2 feature models that we try to create now, and we'll need to delete this for the code to work. So right-click, delete the model, and now run evaluation MLP. Should work. We got a new model with 26.38% accuracy. Now, if I run this again, it's going to try 5,000 more times and maybe get a better version. Or not. Let's try one more time, see if we're lucky. And we got 29% accuracy with this one. And you'll notice that this decision boundary plot is generated really quickly now, because doing the feed-forward algorithm is much faster than doing the nearest neighbor search. So we could go in Node here in the run evaluation MLP and set a higher value for this image size to get a better quality image there. Maybe 1000 is enough. Now let's rerun this. Took a bit longer, but it's done. And accuracy didn't change. So let's try to refresh. And we see now this network with just 2 nodes here, the width and the height, just 2 features and the input layer. And the output, it looks different, but it seems again the same kind of scenario with just 3 things considered: the car, the tree, and the bike. Now let's toggle again. And this is now the decision boundary plot. And it looks interesting. It has here at the top the tree section, and then the bicycle section, and then the car section. This is confusing me with the pencils, so let's go back to viewer HTML and put all the testing samples now. I'm going to comment out this filtering from here. Refresh. And now we can see this decision boundary plot. And every one of these trees here in the green region is classified correctly. Every one of these bikes here is classified correctly. And every one of these cars here is classified correctly. But a lot of misclassifications happen. There is a pencil region here. And this car is in the pencil region, so why didn't it show up in our confusion matrix? Oh, it did. It has a 1 here. I didn't notice it. And the tree should be there as well, apparently. And there it is. Herminio's house is also there, classified as a car. Nice. Now let's try one more thing and see if we can add the hidden layer here and if we get any difference. In our run evaluation MLP, at the top, let's say we are going to add 10 nodes on a hidden layer and see what happens. Because we redo this evaluation and the network that we have at the moment doesn't have those, I'm gonna have to delete again this model here. And rerun the evaluation. A bit worse accuracy. Let's try to improve it. Give it 5,000 more tries. Doesn't seem to work. One more try. Maybe we're lucky. And we are not. Let's just keep it like this and see what we have on the page. So this is how the new neural networks looks like. And if we toggle the input and we draw something really wide, you can see now this lighting up. Let's make it also tall, so this will light up. And a lot of things are lighting up here in the middle in interesting ways when these properties change. So it's a more complex model, but not a very good one. It also seems to now prioritize 2 things here. Let's see the decision boundary plot. Let's close this input. And I don't really see it so well. Let's keep just the decision boundary plot now here. And I'm going to add again this filter because it keeps that plot in a kind of squarish aspect ratio because that's where the pencils are. There's no Herminio's house to stretch things. So let's hide the samples and refresh, toggle the output. That's how it looks like. Let's re-add all the features one last time, now with this hidden layer there. So in feature functions, I will remove this comment from here. And here we go down and feature extractor, It's done, and now let's run evaluation MLP. Oh, I forgot to remove that model that we had last time. Delete. And now run evaluation MLP. Refresh, and now the input layer is more complex again. Still this kind of bad looking confusion matrix. And this one is unreliable now because we just showed the first 2 dimensions there. Now, optimizing this with the current strategy is not going to work well. You could wait for it to randomly try a bunch of different values, and you could leave it overnight or something. You will get better values. But next time, I'm going to teach you how to use Python to get the values with more complex optimization algorithms. The neural network is now there, but it needs to be optimized better. And the typical way of doing this is with the backpropagation algorithm. I don't have a good way to teach it, and the best video I know on the topic is from 3Blue1Brown. So go watch it. What we'll do is use backpropagation in Python. There are some JavaScript implementations as well, but I want you to see that you can combine programming languages like that and use their strengths when needed. Python has many machine learning libraries. We'll continue to use scikit-learn because we used it in phase 1, but others are more popular nowadays, I think. It doesn't really matter. All we need is something that gives us good weights and biases, and paste them into our model. Now, get ready to blur the lines between programming languages. Make sure you have Python installed for this next part. Last time we used Python, we were in this Python folder, and we had this knn.py and some functions for reading the CSV features. We're going to make a new file similar to this knn, but we'll call it MLP. So copy and paste it here, rename MLP, and it's the same thing as knn for now. But we will include from this scikit-learn library, not from neighbors this time, but from neural network, and we import the MLP classifier. It has an implementation of it already. Then here we write MLP, 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 everything looks the same. But here we are going to have this MLP classifier, and these parameters don't fit anymore. Instead, we should pass the number of hidden layers, and actually how many neurons should be on each hidden layer. So we have to use a tuple for that, and at the moment I just have here 10, because I want it to be the same kind of structure as we used last time in JavaScript. So let's pass here this hidden, and now we can test. So let's open a terminal. We normally worked inside of this node directory, so if you're still there, make sure that you're going to run this Python code by first going outside. So Python, the running command, and then going outside of the node folder, and then Python mlp.py. This is what will run this code. And looks like we're getting something really good, 61%. And an error here saying something about the optimization not being finished yet. And that's because there is a parameter that we can set to this classifier that it can iterate longer. So I'm going to pass this, set here max iter to 10,000. And let's save this and run this again. Now we get 66%, almost 67%, which is really good. Now, if you're going to run this code again, it's possible that you're going to get another accuracy here. Like now, it changed slightly. And that's because it also uses randomness of some kind. But if you want to have predictable results here, you can pass another parameter and fix the random state. It's still going to use randomness, but now the randomness is predetermined, if that makes sense. So saving this and running this gives us some value now, maybe 61%. I guess we weren't as lucky as we were before. But it's consistent. And if you change this value to something else, you will get some other accuracies there. Some of them will be more lucky, some of them not, depending on your luck, I guess. But I'm just going to fix one here. I don't really care about the accuracy that much. 60% is definitely very good compared to what we were getting with random chance. But okay, this is just one of these printing in the console things. It's not so great. How to get it to work inside of our web application and see it in practice? Well, we have to first debug what this MLP object contains. And I'm going to start to print some of its properties, like the intercepts. So let's run this again. And you can see here two values, pretty much. The first value here are 10 numbers, and these are the biases for the neurons on the hidden layer, the 10 neurons on the hidden layer. And these ones here are the 8 biases for the output neurons, the 8 different classes. We can also print here the so-called coefficients. Run this again. And now we're getting something much bigger here. These are the weights. So the weights are much longer than the biases. So these intercepts and coefficients need to go over our model here. If I'm going to format this, we also have to specify neuron counts and the classes here. And then the network, we have the different levels. For each of them, we have inputs, outputs, and then the biases and the weights. So the intercepts and the coefficients are going to be the biases and the weights. We need to fill those in here for all of the levels. But the inputs and outputs, we don't need to worry about that because these are going to come in as a given. The inputs and the outputs are going to be calculated by the network. So really, we only need to pass here the weights and the biases and also these things that the model requires. So let me show you how to do that. Let's remove here this. And I'm going to need to know what these classes are. Let's define them in a list. Car, fish, house, tree, bicycle, guitar, pencil, clock. And now let's start forming our object. It's going to be this JSON object. And the neuron counts. Now, the values from this are going to be the length of x of 0, where we have the number of features, basically, for the input layer. And then the hidden, which is defined up here, followed by the length of the classes, which we just defined here. Then the classes, I'm just going to pass this object directly. And then the network, this is going to be a dictionary here with levels, which is going to be an empty list. And now these network levels is what we have to fill in from the intercepts and the coefficients. So I'm going to loop through all of the coefficients like this. And let's define the level with the weights, and I'm going to convert these coefficients into a list, and I'm going to do the same thing with the intercepts, like so. And inputs is going to be just zeros. I'm just going to multiply them by how many coefficients there are, and outputs, I'm going to multiply them by how many intercepts there are. So these are just zeros. And then we need to append this level to our JSON object network levels. So this is a dictionary, so we refer to the keys like that and append the level. Now, Python does have a JSON module, and we can import it here and use it to define a JSON object with an indent so we can read it more nicely. And now what we have to do is write this JSON object into our file here that we will use in our viewer. Both the one here in the models and the one in JS objects here. I will modify both of them in Python so we don't have to worry about it. Let's open the one in data models, model.json for writing. And write the JSON object. Now I'm going to copy this also for the JS object, the JavaScript object, and this is going to be in common JS objects and model.js, like that. And when we write it here, we also need to concatenate that string to assign it to an object. So const model is equal to, and let's concatenate with this, and then here at the end, concatenate with a semicolon. And now when we run this Python code again here in the terminal, let me first clear it up a bit. So if I'm going to run it again, it lists here the accuracy, but our models, the model.js file here, and also the model.json file here should have updated with the new values. So now the weights are going to be calculated from Python, and the biases come from Python, and the inputs, outputs are turned into zeros. If we did everything correctly, then now we can run this run evaluation MLP, and it's actually now trying to improve that model if it can, but most likely it cannot. And it's done. Let's see it now in practice. I'm going to refresh the page. And there you have it, a neural network that now has 61.79% accuracy. And if we toggle this, we can see this confusion matrix looks much nicer. Quite similar what we got with the KNN actually. And the decision boundary is not going to help us much in these high dimensional spaces. But we now have a neural network here that actually is able to recognize things quite nicely, quite well, with 61.79% accuracy. Nice. Okay, it's quite good actually. Now, I didn't plan to teach too many things about neural networks here. I plan to do that in phase 3 of my self-driving car course, after phase 2 is done. But let's try to investigate a bit using just 2 features again, so we can see also this decision boundary plot coming from a good neural network. I'm going to go here inside of common feature functions And let's keep just the width and the height again. And now let's do feature extraction with these two features only. And now let's do the training with Python. So we got a 42.3% accuracy with just two features, which is comparable to the KNN we got previously with just two features. Now let's run the evaluation so it generates also the decision boundary plot. And something looks off. This 31.7% accuracy, what happened? It was supposed to be 42%. Why did it drop so much? Well, turns out the reason is the activation function that this MLP classifier uses by default is the rectified linear unit. And we will need to implement this rectified linear unit into our JavaScript code for it to be fully compatible. Let's do this. I'm going to open here the network.js. And here where we're computing the outputs, we need to apply this ReLU activation function. Here goes. Done. It's just a maximum between 0 and that other value. It doesn't like to have negative values here. So let's save this and now run this evaluation again. I should really turn off this trying to optimize here. Let me go to run evaluation MLP, and here where we're doing the fitting, I'm just going to decrease this value by a lot. Let's say I will remove it so it defaults back to 1000. It's going to be almost instantaneous. Okay, and now you actually see here the accuracy being 42.4%. So the same as we got in Python. And now let's test on the web page. There's the network. And if we toggle the output, it looks okay for just two features, the width and the height. And the decision boundary plot looks like this. It's much more simple than the complex one we got previously from KNN. But otherwise, it's comparable in many ways. Like a section here for the pencils and one for the fish and this one for the clocks. I can obviously tell that they are there. Now, these activation functions, they are several of them, and you can check the documentation on the scikit-learn library webpage, for example. If we go back in Python, we can actually pass them here. We could say activation set to hyperbolic tangent, for example. And this is going to be, again, one of those really difficult ones to implement. But let's see first if it works. So let's try the hyperbolic tangent now in Python here. It's not a big difference, but I want to show you just how the decision boundary looks different. Now let's implement this hyperbolic tangent in JavaScript. And the good news is it's already there. The math library has an implementation of it, so we can just call it directly here and remove that 0 that we used for the max previously. Now let's run also the evaluation here so that we get the new decision boundary plot. And if we refresh, toggle the output, and again, you'll see that it looks more curved because of what we just did. I think this way of learning is really nice, and if you're going to go deeper and study the mathematics behind the things, you're going to have an intuition of what to expect. But yeah, let's add all the features again. and see what effect this hyperbolic tangent has on all of them. Wow, we got to 68% now. To see this on the web page, we don't really have to run the evaluation anymore, because the model is already there, and with so many features, the decision boundary plots are useless pretty much. So when we want to optimize, we can just run this Python code and open the viewer. Unless we change the features as well, then we have to do the feature extraction again. If we refresh the viewer, this is what we get. We have now this neural network here, and it starts to have kind of a structure. It's not anymore completely random if you look at the links. The matrix here looks better and better all the time. Almost 70% accuracy, so that's quite good. And this, I won't bother with it anymore. We can check also down here in the testing section to see that a lot of blue started appearing recently. And in many situations, all the drawings from one person are recognized. Starts to feel like this is actually doing something good. I decided to include this section on deep neural networks, so you don't ask something like, when are you going to teach us something cool like deep neural networks? Well, you already know how to use them. It's just a neural network that has many connections, many hidden layers, and so on. I'm also going to teach you a way to go from the 5 features we've been using to 400 features. But as you can see from how long this video is, it won't be rocket science. We'll just use the pixels themselves as features. So it won't really be a deep dive this time. We'll only go skin deep. Inside of feature functions, I'm going to comment out everything here, really. And we will implement a different kind of code structure here. It will break what we have previously, so keep a backup of that if you want to compare. But we won't do many changes today, so you can also revert if you pay attention. Now, what we do here is we open up an object with the name pixel array, so this will have all the features coming from one function call. And the function is going to be called on paths, but then it's going to return all the pixels from our getPixels function, which we call on the paths, but I'm also going to specify a size because I don't want to have 400 times 400 pixels. That's going to be a lot of pixels and they are not necessary. We can figure out what the drawing is even from a small drawing and it's going to be more efficient. So in my case here, I'm going to use a small 20 by 20 canvas. Now let's close these. And this is going to be a feature vector with 400 dimensions. Now we need to change some things in the code to work with this new structure. And we're going to go to node feature extractor JS and comment out this line here. And instead write this new one that only takes out the values of calling the first and only function that we get from the feature functions in use. So we call this one here directly on the paths and get the values, assign them to the point. Now, this feature names at the moment would just say pixel array here, and that's not good. They need to be many of them, 400 of them. So what we do here is comment out this line, and I'm going to write this new one where we create an array the same size as the first sample's point length, and we fill it with zeros. Or anything you want, really. We can fill it with an empty string like this. It just needs to have 400 items for the code to work. Now, for the web to work, we also have to do this for the real-time calculation of the features there instead of this mapping here. And here we can just take the first function and call it on the paths, like so. Now this should work. If we open now the terminal, we can extract these new features. Let's go to the node folder and then extract these new features. And let's have a quick look what they are. Inside data, dataset. And now let's, for example, open these CSVs. They are easier to read. You can see at the top the feature names. They are those empty strings separated by commas. And there are many of them, 400 of them. And last thing is still the label. And then here there are pixel values, visible pixels here, and some pixels may not be fully visible because of this anti-aliasing, but some pixels are completely invisible. And this is the whole very long feature vector for each individual sample. So can this work? Well, if I'm going to optimize now with Python, it seems it does. And we're now at 70, almost 75%. Wow. Let's take a look in the web page. And we now have this beast here with all these connections here from each individual pixel, all 400 pixels of the small 20 by 20 size image. And this is the new accuracy. This is the new matrix here, and it looks really, really good, doesn't it? This we already said we don't look at anymore with these high number of dimensions there. And if we try to make a new input here, it seems to work. And I made these nodes here very, very small in the visualizer if they exceed a certain value. Now, if you want to get an even nicer visualizer here that somehow modifies also the weights based on the activation of these bottom neurons here, then you could go in the visualizer and go to draw level. And here we're drawing these weights between the inputs and the outputs. So they are the lines, and we set here the value, the RGBA of the weight value, but we can multiply this by the inputs of I. And this is going to make that connection disappear if that pixel is off, or be there present if the pixel is on. Because of that anti-aliasing, it could be also some transparent value. So let's save this, refresh, and now everything is off here. But if we start drawing something, we start to see there those connections appearing. And I think it's interesting. It makes this a much more dynamic system. This is not a pencil. Oh, come on. Maybe if we give it some more detail, like... Okay, now it's a fish. Great, but this is not yet a deep neural network because it just has this one hidden layer. Let's go deeper. We're going to go to our Python script. Let's put 100 nodes on this one hidden layer for now, and then we try more later. So let's optimize again. 82% accuracy. We broke another barrier there at 80%. Let's see how this one looks like. And this is it. Wow, look at that. Now this system starts to become slow because of this visualization here, but also because the model becomes more complex and there are more calculations. I think we can try with 2 hidden layers so that we do get some deep network, even though deep means a lot of them, but you get the idea. Let's add 100 more. %. Not a very, very big improvement, but it's still an improvement. Now let's see how it looks like. So now we have this. And if we draw something, a lot of crazy stuff happening there. And it is a house. It seems to be quite reliable. Like after it's a house, it's a house here. Well, let's see our confusion matrix one more time. And yeah, this looks really good. And let's have a look also at the classifications. Very few of them are not blue right now. Now, people have different views here. Some like the small models with relatively few features and consider big models like what we just built as a waste of resources. But others think they're worth it because you can teach them pretty much anything without the pain of tailoring features one by one. The problem is, it's really hard to explain why the system works a certain way if the model is so big. Hope you liked the course. Let me know if you want to see more. Like, I didn't teach you anything about clustering yet, and it's an important part of machine learning. Or we could try to identify the person who is doing the drawing instead of what is being drawn. Maybe we can make a really sophisticated authentication system like that. What do you think? Go in the poll in the description and vote your favorite. See you guys.